Okay, so derivation of PV equals a third nm c squared bar, where the symbols mean what it says in the box. So the particles in an ideal gas are creating pressure by colliding with the walls of the box. They're moving in random directions with a range of speeds. So we've got a box like so. Dimensions are all L, and it's full with these molecules of an ideal gas all whizzing around, random speeds, random motions, and some of them are colliding with this face here. The instantaneous total force on any wall is constantly changing because you've got billions of them, and at any one instant in time there are different numbers colliding with the wall. So assumptions made when defining an ideal gas. We've discussed this quite a few times. You've got the time taken for the collision is very small compared to the time between collisions. The forces between the molecules are negligible except during the collision, and the collisions are perfectly elastic. So if we do with the first two bullet points first, if you like to work in pictures or in graphs, you've got force in newtons, you've got time in seconds, and whilst the molecule is moving from one side of the box to the other, the force is zero. We're just going to look at one molecule interacting with the wall, we're ignoring all the others, and then it hits the wall, the force shoots up, but the time taken for the collision is negligible, so it's a very small delta t. And then it goes back across the box after colliding with the wall, hits the other side, and then it comes back and it does exactly the same again. So the force is like this. Okay, so that's a little picture for the repeated collisions with the wall where delta t is really small, and this time here is very big in comparison. The time between collisions is much bigger. And then the last bullet point, perfectly elastic, it's there, it hits the wall, it bounces back, and if it's perfectly elastic, then there is no loss of kinetic energy. Ke before collision equals Ke after. So if that was before with velocity v, if the kinetic energy stays the same, the velocity must stay the same. So if it comes back the other way, then the velocity would be minus v. So K before equals K after. Moving on to, so we've already discussed the time for the collisions is very small. It's not known, it's not specified, but actually that's not a problem, because we're interested in the time averaged force. We're not interested in this rapidly fluctuating instantaneous force. We're interested really in what's the average force over a period. We may as well choose sort of 1 second, hadn't we? So the idea is this. You've got the graph from the other page, these, very small delta t's, these big f's as time goes on. But actually, if that was, say, 1 second here, at that point there, this just equates to something like this. If that's 1 second there, and that's still t, then the average force is going to be much smaller, and it acts for the whole second instead of this completely repeated big force for a small time. We've got a smaller force, but for a longer time. And the key is this, isn't it? If we worked out these two areas, they would have the same area, because the area is equal to the total change in momentum. So what we're saying is the actual change momentum is these rapidly fluctuating these rapid big forces for small time, but the change in momentum is the same as a smaller force for a long time. Okay, so we're interested in this idea of time averaged force. So, the actual derivation, so to the nitty-gritty. The other bit is just to get you thinking, to get you sort of warmed up to what's going on in an ideal gas. But let's look at the derivation in 6 easy steps. We do it by looking at one molecule moving from one side of the box to the other and then back again. So if we just look at a cross section of the box, we've got our one molecule, it leaves that side, it travels over, it hits the wall, it's rebounded back, perfect elastic collision, and it comes back to this side. So at this point here, if we choose its momentum to be mc, where c equals speed, I suppose we should say velocity really, shouldn't we, if it's momentum. So its momentum is mc going that way, but when it bounces back and it comes back this way, then it's minus mc, because the velocity has changed direction, and as you know it's a vector. So if we're looking in the change momentum, the change momentum equals, well, we all know you do final minus initial, so the final momentum is minus mc, minus the initial momentum, which is mc, so that's where you get your change momentum as being minus 2 mc from. So that's the first step. You do the change momentum of one molecule when it's hitting the wall and going back. Okay. We're then interested in the number of collisions per second. So how many collisions per second are there? Well, we know the journey. It's going from there, it's hitting this wall, and then going back again. So that's the actual journey. These are the two walls. And I want to know how many collisions we get on this wall per second. Well, let's work out the time between the collisions then. It hits that wall, and then before the next collision it's got to go all the way over there and all the way back again. So the time between collisions is equal to, well, it's the time to travel 2L, because that is from one side of the box to another, and we know that's length L. So that is equal to 2L over c, where c is speed. Just to insult you, to remember, time equals distance over speed, if you rearrange the speed formula. So that's the time between collisions, 2L over c, but we want the number of collisions per second. So therefore, number of collisions per second is equal to 1 over that. 1 over 2L over c, which is equal to c over 2L. So that is our important value, isn't it? The number of collisions per second is c over 2L. Well, we're moving towards trying to work out what the pressure is. Well, pressure is force over area, so we've got to somehow turn this change momentum into force, haven't we? To do that, we need to know the total change momentum. This step's easy. Step 1 was the change in momentum for one collision, which, if you can remember, was minus 2mc. Or you have to rewind the video. Times by the number of collisions per second we've just got there is c over 2L. And if you do that, you get minus, the 2's cancel, you get minus mc squared over L. So that's the total change momentum in 1 second for this molecule. Change for one collision times by the number of collisions in a second. That's going to be a pretty important number, as you'll see in this derivation. So, where do we go from there? Well, we're now into Newton's laws. We've got a change momentum, and we've got actually the change momentum per second. Well, as it says here, Newton's second law says force equals rate of change momentum, delta P, change momentum over change in time. Well, we've just worked out the change momentum. The change in momentum, delta P, is minus mc squared over L, and the change in time was 1, because we worked out the change in momentum in 1 second. So it just stays the same. The force is minus mc squared over L. Now, the thing that's been having its momentum change so far is the molecule. This is the mass of the molecule, and it's the force on the molecule that changes its momentum. We're interested in the force on the wall, because we want to know the pressure pushing on the wall, the pressure that comes from these billions of molecules. But that's dead easy, because Newton's third law, action and reaction, if the force on the molecule is equal to minus mc squared over L, then the force on the wall, so this is the force on the molecule from the wall, and the force on the wall from the molecule is the Newton's third law pair. So the force on the wall is the equal and opposite force. So if it's opposite, then the minus disappears, but the size is the same, the magnitude is the same. So that conveniently gets rid of our minus for us. We're interested in the force on the wall is mc squared over L. We're nearly there, we're nearly there. This, remember, so far, is the force on the wall due to one molecule travelling at speed c with mass m. Now, of course, we're not dealing with one molecule, are we? We're dealing with n molecules. Remember at the start, on the first page, we said there are n randomly moving molecules and they've got a range of speeds. So if we focus in just on the right-hand wall now, yeah, we've got that right-hand wall and it's being bombarded by molecules. And we're interested in these n molecules. So we've got the force due to 1 equals mc squared over L. But due to n molecules, that becomes F equals a third n mc squared bar over L. So what's happening here then with this third and this c squared bar? Well, let's go for that first. We've got c squared for that one molecule, but they move with a range of speeds. So the bar means the mean. It's the average, but we're going to be fussy. It's A level. It's the mean of the square speeds of all the molecules. The mean square speed. So we can look at all n molecules. The third, well, the third is because it's only a third n, because we're looking at the pressure on the right-hand side. So we're interested in third n because the random motion means that only a third of the total, a third of n, are acting left to right, which is the direction we're interested in. A third are acting back to front, from the front face to the back face, and a third are acting up and down. So we're only interested in the pressure in the left to right plane, so we're interested in a third n. That's a bit of a fudge, okay? So C, Advanced Physics by Tom Duncan, 4th edition. And that gives a more mathematical proof of this third n. But it does work. We're considering a third of the molecules because of the random motion is creating the pressure we're interested in. That book is available from Mr. Long for a small charge. Okay, so we're nearly there. So we've got our expression for force from these n molecules now. Remember, we're dealing with an ideal gas. They've all got the same mass, but they've got a range of speeds. And just to remind you, we're starting off from the last page with that force is equal to a third n m c squared bar. The bar shows that it's the mean square speed over L. This is the force on the right-hand wall. But the derivation is for a pressure relationship, not force, but dead easy, back to sort of the 12-year-old physics. Pressure equals force over area, so that equals the force, third n m c squared bar divided by L, all divided by the area. Well, again, fed up of drawing this, but there's our wall and it's L by L, so the area is L squared. which becomes pressure equals a third nm c squared bar over L cubed. And we're nearly there, that's supposed to be L cubed, which gives us a third nm c squared bar over V, because L cubed for the original box is the volume of the box. And we have finished. PV, bring the V up here, PV equals a third nm c squared bar. That is the formula that we were trying to derive. Thank you very much.